part C introduces a second circle, C2, with centre 11, 14. And we're given that a point Q lies on C1 and R lies on C2. And we have to find the shortest possible length of the line Q to R. I've drawn out the diagram roughly just to give an idea of what's happening there. And at the moment I've made a note that the circles aren't touching. What I'm going to do first of all is find the distance between the centres of the two circles, and in doing this we can set up a right angled triangle, horizontal and vertical distances. In horizontal we go from an x-coordinate of 3 to 11, which is a distance of 8, and minus 1 to 14, a distance of 15. Applying Pythagoras' theorem, we'll call the distance between the two centres x, so x squared will equal 8 squared plus 15 squared. So x squared is equal to 64 plus 225. X squared is equal to 289, and rooting, you should find that the distance x is equal to 17. Now this is quite interesting because this actually proves that the circles don't touch. They're actually apart, because if you look at the sum of the radii, we add those together, we get 5 plus 8, which is equal to 13. That leaves a difference of 4. So what we've actually got here is a situation where we can show the shortest possible length. If we look at the distance between C1 to its circumference, that would be a distance of 5. The distance between the centre of C2 and its circumference would be a distance of 8, making 13. So if Q was to be the point marked there, and R was to be the point marked there, the difference between 13 and 17 is of course 4, and this really has to be the shortest distance between Q and R. So QR has to equal 4. This would only be being able to be calculated or seen if you'd actually drawn the diagram out.